Welcome. Today, we're going to demonstrate how to solve a system of equations involving two unknowns by using the ideas from our previous videos. So the demonstration is using Python programming language. And the first thing that I'm going to do is to import NumPy, which is the library that is needed for matrix operations within the Python programming language. The next thing I'm going to do is to store the coefficients of x and y in matrix A. The way I will do it, I'll say A is equal to np dot mat, and then open and close the parentheses, and then open and close brackets, and then specify now the elements of this matrix. So that will form the first row. It consists of the elements 1 and 2. Notice that those are the coefficients of x and y in the first row. The second row consists of the coefficients 3 and 4. As you can see, those are the coefficients. And next, we're going to type A to just make sure that we have stored this correctly. And it shows that matrix A has been stored correctly. The next thing we're going to do is to store the right-hand side elements in matrix B. Matrix B will be sort of a raw vector, but we'll store it as a matrix. So we'll have np.mat, and then open and close the parentheses, open the brackets, and open the brackets again, and store 1, 2. So, and type B, press Control Enter, and it shows that we've stored matrix B correctly. Now we have what we need. We have stored the coefficients of x and y as matrix A, and stored 1 and 2 as matrix B. The next thing we're going to do is to follow the procedure that we outlined. So the first thing we're going to do is to find the determinant of matrix A. But before I do that, let me point out that the solution to the system is, let's call it sol, which is equal to A inverse times the transpose of matrix B. This idea, you can try to understand it more robustly by performing AND calculations. You will notice that if you were to go to the theory of linear algebra, you will be able to see that if we have a matrix, assuming you're trying to solve a system of equations like this, in the end, the solution that you get must be consisting of this type of solution. And we can demonstrate it by saying A times, let's say, x, where x is our matrix for the variables and is equal to b. If we multiply A by its inverse, so we multiply the left-hand side by the inverse and multiply the right-hand side by the inverse, you will notice that the product of A and A inverse is the identity matrix. And when you do that, this gives us the identity matrix times x is equal to A inverse times B. And in our case, since we're dealing with B as a column vector, we have to have it as the transpose. And so the identity matrix times matrix X will give us X. But X is what? It is the transpose of X and Y. So that gives us the solution. So the right hand side is the solution. And so that's why we're saying our ultimate solution is A inverse times the B transpose. So let's go through the process now. So the first thing we're going to do is to find the determinant of matrix A. Because remember the process of finding the inverse of a matrix. So we'll say A, or determinant of A, is equal to np dot linear algebra, meaning we're going to the library that we imported NumPy and then say determinant of matrix A. Say that A. And notice that we have the determinant. If you look at our previous video, this was the determinant, although it did not have this level of precision. So I'll round it to one decimal place. And it gives us the determinant. The next thing we did was to find the A star matrix. And we say the A star matrix is found by switching the elements on the leading diagonal. So we should have 4, 1. So we're switching the elements of matrix A on the leading diagonal and then negating the elements on the other diagonal. So we should have, so this should be 4, 2. And the other one is -3, 1. So we're going back to matrix A and switch the elements on the leading diagonal and negate the elements on the other diagonal. So notice that we have the elements 4 and 1 switched in matrix from matrix A, and the elements that are on the other diagonal are negated. So that's A star matrix. The next thing you do after that is to find the A inverse. The A inverse matrix is found by multiplying the reciprocal of the determinant of matrix A by the A star matrix. So A underscore inv is our A inverse matrix. And you can see we have stored it correctly. And that is what we expected. So if you look at our previous video, that's what we found. The next thing you do after that is to now find the check. Let's check that we have the correct inverse. So if we multiply matrix A by its inverse, A underscore inverse, what should we get? Well, what should our result be? It should be the identity matrix, the 2 by 2 identity matrix. And correct, we have it. The next, we can also check by pre-multiplying A by its inverse. So we can say A inverse times matrix A, and it is correct. We see that we have the same identity matrix. So now, since we have the correct matrix, the A inverse matrix, the last thing we're going to do is to find our solution. And our solution for the system is A inverse times B dot transpose. Remember, that is the solution for the system. And if we do this, we have the correct solution. How do we know it's correct? Let's see. So the solution is what? X has to be 0 and Y has to be a half for this system to be correct. So let's see. So if I replace X with 0 and Y with a half of 2 is what? 1. So the first equation is true. If I replace the value of X in the second row with 0 and the value of Y with a half, the result is 2. So that's correct. So we have the correct solution. And that concludes the process. So we know the system that we were given is actually a system with a solution, meaning the two lines intersect at the point. So the two lines intersect at the point 0, comma a half. So if you graph these two lines, you should be able to get the point of intersection to be X to be 0 and Y to be a half. And this concludes the process of solving a system of equations, two equations with two unknowns using Python programming language and Anaconda.